Everyone. So today we are going to discuss about the case study on excessive dislocation present in silicon wafer. So how we have detect defects in the silicon wafers. Okay, how we can use computational methods to detect the defects in the silicon wafer. Okay, so our case is this is our case study. So imagine, if we manufacturing the silicon wafer of worth 1,000 rupees, okay. So if there is a very tiny dislocation is present in that material, so it will destroy its function, right? So that's why we have to find the dislocations present in that material, okay. So what's meant by dislocation? So this is the displacement. Okay, this is the type of defect. Okay, so this is called as line defect. Okay, so in crystals we have many type of defects. Okay, one of the defect is line defect. Okay, so line defect, surface defect, and point defect, and volume defect. We have many type of defect. Okay, so dislocation is under the line dislocation. Okay, so in line dislocation we have two types. So edge dislocation and screw dislocation. We have two types of dislocation. Okay, so why we have choose silicon wafer here? So because silicon, so in semiconductor industry, so we have semiconducting materials mainly we have used silicon wafers. Okay, because it has very high crystal order. Okay, so in suppose the defect is present in that silicon wafer, so it will decrease the, so it will damage the crystal order. That's why, so we have to find the defect in that material. Okay, so here we have to discuss about the, so how computational methods will detect the defects in the material crystal structure. Okay, so let's start.
So silicon wafers are the fundamental building blocks of modern semiconductors. These devices such as microprocessors, chips and sensors. These wafers are typically manufactured as high purity crystal silicon using process to ensure a nearly perfect crystal structure. And this structure has some while wafer slicing or thermal processing, they get some defects called dislocation. This dislocation may be, if it is very small, this is actually tolerable. But if this has more density, this can affect the devices a lot. And by understanding the importance of the dislocation and detecting them, we can improve the quality of the chips and other devices by studying about this topic.
Very good. Next.
Problems arising due to excessive dislocations. First one is leakage current. Dislocations introduce energy levels within the band gap of silicon. So this causes the recombination generation energy, allowing the unwanted current to flow through it. Effects of this is high standard power consumption, reduced efficiency in low power devices, poor performance in CMO devices, and reduced carrier mobility. Charge carriers like electrons and holes move through the crystal lattice. Dislocation scatter these carriers, reducing their mobility. This affects the increased resistance, slower switching speed, and reduced overall device performance. Enhanced recombination, this is also an important one. Dislocations acts as recombination centers where electrons and holes recombine prematurely. Effects of this is reduced minority carrier lifetime, poor performance of photodiodes and solar cells, lower gain in bipolar junctions, transistors. Next one is junction breakdown and reliability issues. In PN junction, dislocations create localized electrical field enhancement. Effects of this are relative breakdown at lower voltage, increase in noise, low term reliability degradation. Next one is reduced manufacturing yield. As dislocation density is high, in certain wafer regions, devices fabricated in those areas fail electrical wiring and yield percentage decreases. Another one is manufacturing cost increases significantly.
How to detect dislocations in computational tools, DCA simulations, simulate semiconductor device behavior. We can introduce defect parameters, compare ideal versus effective wafer performance, and analyze leakage current, carrier item, and based defect detection. Uses image processing and wafer inspection images, and defect patterns are automatically detected, and improves quality control in fabrication techniques.
Okay, good. So these are the computational methods. So AI tools are used to detect the defects in the crystalline structure, right? Okay, next.
Advantages of computational detection. Computational detection means using computers, softwares, and simulations to find defects in silicon wafer. It helps engineers check chips easily and quickly. The advantages are more accurate, saves time, easy problem, yearly problem detection, saves money, predicts problem, no damage, easy installation, and less event.
Okay, so these are the advantages of AI. So we will predict the predict 100% prediction, right? Okay, so that.
Plus the controls reduce electrical improvement, reduces carrier lifetime, causes device failure, increase leakage current. In the using computational techniques like PCAD, FTA and DFT simulators, it predicts, manage and analyzes the impact of this defect during manufacturing. This improves the product quality, reliability, and aid in semiconductor fabrication.
So good. So now, we conclude that. So how the AI tools can be used to dislocate, find the defect in the materials, right? So now we discussed all the factors. Okay. So thank you all.
Thank you, ma'am.
Every